Relations Chapter 9 Copyright McGraw-Hill Education. All rights reserved. No reproduction or distribution without the prior written consent of McGraw-Hill Education. Chapter Summary Relations and their properties and area relations and their applications not currently included in overheads representing relations closures of relations not currently included in overheads equivalence relations partial orderings. Relations and their properties Section 9.1. Section Summary Relations and Functions Properties of Relations Reflexive Relations Symmetric and Antisymmetric Relations Transitive Relations Combining Relations Binary Relations Definition A binary relation R from a set A to a set B is a subset R A times B. Example: let A equals 0, 1, 2, and B equals A, B, 0, a 0, B, 1, a 2, B is a relation from A to B. We can represent relations from a set A to a set B graphically or using a table. Relations are more general than functions. A function is a relation where exactly one element of B is related to each element of A. Binary relation on a set definition. A binary relation R on a set A is a subset of A times A or a relation from A to A. Example: suppose that A equals A, B, C. Then R equals A, B, A, C is a relation on A. Let A equals 1, 2, 3, 4. The ordered pairs in the relation R equals A, B, A divides B, R, 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 4, 3, 3, and 4, 4. Binary relation on a set. Question: how many relations are there on a set A? Solution: because a relation on A is the same thing as a subset of A. We count the subsets of A times A since A times A has n2 elements when A has n elements, and a set with m elements has 2 meter subsets. There are subsets of A times A, therefore, there are relations on a set A. Binary relations on a set. Example: consider these relations on the set of integers. R1 equals A, B, AB. R4 equals A, B, A equals B. R2 equals A, B, A greater than B. R5 equals A, B, A equals B plus 1. R3 equals A, B, A equals B or equals minus B. R6 equals A, B, A plus B3. Which of these relations contain each of the pairs 1, 1, 1, 2, 2, 1, 1, minus 1, and 2, 2? Solution: checking the conditions that define each relation, we see that the pair 1, 1 is in R1, R3, R4, and R6. 1, 2 is in R1 and R6. 2, 1 is in R2, R5, and R6. 1, minus 1 is in R2, R3, and R6. 2, 2 is in R1, R3, and R4. Note that these relations are on an infinite set and each of these relations is an infinite set. Reflexive relations definition. R is reflexive IFF A, R for every element A written symbolically. R is reflexive if and only if X, U, X, R. Example: the following relations on the integers are reflexive. R1 equals A, B, AB. R3 equals A, B, A equals B or equals minus B. R4 equals A, B, A equals B. The following relations are not reflexive. R2 equals A, B, A greater than B. Note that 3, 3. R5 equals A, B, A equals B plus 1. Note that 3 does not equal 3 plus 1. R6 equals A, B, A plus B3. Note that 4 plus 4, 3. If A equals, then the empty relation is reflexive vacuously. That is, the empty relation on an empty set is reflexive. Symmetric relations definition. R is symmetric IFF B, A, R whenever A, B, R for all A, B A written symbolically. R is symmetric if and only if X, Y, R, Y, X, R. Example: the following relations on the integers are symmetric. R3 equals A, B, A equals B or equals minus B. R4 equals A, B, A equals B. R6 equals A, B, A plus B3. The following are not symmetric. R1 equals A, B, AB. Note that 3, 4, but 4, 3. R2 equals A, B, A greater than B. Note that 4 greater than 3, but 3, 4. Our 5 equals A, B, A equals B plus 1. Note that 4 equals 3 plus 1, but 3 does not equal 4 plus 1. Antisymmetric relations definition: a relation R on a set A such that for all A, B, A, F, A, B, R and B, A, R, then A equals B is called antisymmetric. Written symbolically, R is antisymmetric if and only if X, Y, R, Y, X, our X equals Y. Example: the following relations on the integers are antisymmetric. R1 equals A, B, AB. R2 equals A, B, A greater than B. R4 equals A, B, A equals B. R5 equals A, B, A equals B plus 1. The following relations are not antisymmetric. R3 equals A, B, A equals B or equals minus B. Note that both 1, minus 1, and minus 1, 1 belong to R3. R6 equals A, B, A plus B3. Note that both 1, 2, and 2, 1 belong to R6. For any integer, if A, B and a B, then A equals B. Transitive relations definition: a relation R on a set A is called transitive if whenever A, B, R and B, C, R, then A, C, R. For all A, B, C, A written symbolically, R is transitive if and only if X, Y, Z, X, Y, R, Y, Z, R, X, Z, R. Example: the following relations on the integers are transitive. R1 equals A, B, AB. R2 equals A, B, A greater than B. R3 equals A, B, A equals B or equals minus B. R4 equals A, B, A equals B. The following are not transitive. R5 equals A, B, A equals B plus 1. Note that both 3, 2, and 4, 3 belong to R5, but not 3, 3. R6 equals A, B, A plus B3. Note that both 2, 1, and 1, 2 belong to R6, but not 2, 2. For every integer, a B and BC, then BC. Combining relations: given two relations R1 and R2, we can combine them using basic set operations to form new relations such as R1, R2, R1, R2, R1 minus R2, and R2 minus R1. Example: let A equals 1, 2, 3 and B equals 1, 2, 3, 4. The relations R1 equals 1, 1, 2, 2, 3, 3 and R2 equals 1, 1, 1, 2, 1, 3, 1, 4 can be combined using basic set operations to form new relations. R1 R2 equals 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 3, 3. R1 R2 equals 1, 1. R1 minus R2 equals 2, 2, 3, 3. R2 minus R1 equals 1, 2. Composition definition: suppose R1 is a relation from a set A to a set B. R2 is a relation from B to a set C. Then the composition, or composite, of R2 with R1 is a relation from A to C where if X, Y is a member of R1 and Y, Z is a member of R2, then X, Z is a member of R2, R1. Representing the composition of a relation ABCW X, Y, Z, R1, R2, R1, R2 equals B, D, B, B, and MOP. Powers of a relation definition: let R be a binary relation on A. Then the powers Rn of the relation R can be defined inductively by basis step. R1 equals R inductive step. Rn plus 1 equals Rnr. See the slides for section 9.3 for further insights. The powers of a transitive relation are subsets of the relation. This is established by the following theorem. Theorem 1. The relation R on a set A is transitive if Rn R for n equals 1, 2, 3. See the text for a proof via mathematical induction. Representing relations section 9.3. Section summary: representing relations using matrices. Representing relations using digraphs. Representing relations using matrices. A relation between finite sets can be represented using a 0-1 matrix. Suppose R is a relation from A equals A1, A2, am to B equals B1, B2, Bn. The elements of the two sets can be listed in any particular arbitrary order. When A equals B, we use the same ordering. The relation R is represented by the matrix Mr equals Mij, where the matrix representing R has a 1 as its ij entry when I is related to bj and a 0 if I is not related to bj. Examples of representing relations using matrices. Example 1. Suppose that A equals 1, 2, 3 and B equals 1, 2. Let R be the relation from A to B containing A, B, if the element of A, B element of B, and a greater than B. What is the matrix representing R, assuming the ordering of elements is the same as the increasing numerical order? Solution: because R equals 2, 1, 3, 1, 3, 2, the matrix is. Examples of representing relations using matrices. Cont. Example 2. Let A equals A1, A2, AA3, and B equals B1, B2, B3, B4, B5. Which ordered pairs are in the relation are represented by the matrix solution? Because R consists of those ordered pairs I, Bj with Mij equals 1, it follows that R equals A1, B2, A2, B1, A2, B3, A2, B4, AA3, B1, AA3, B3, AA3, B5. Matrices of relations on sets. If R is a reflexive relation, all the elements on the main diagonal of Mr. R equal to 1. R is a symmetric relation if and only if Mij equals 1 whenever Mji equals 1. R is an antisymmetric relation if and only if Mij equals 0 or Mji equals 0 when I does not equal j. Example of a relation on a set. Example 3. Suppose that the relation R on a set is represented by the matrices R reflexive, symmetric, and/or antisymmetric. Solution: because all the diagonal elements are equal to 1, R is reflexive. Because Mr is symmetric, R is symmetric and not antisymmetric because both M1, 2 and M2, 1 are 1. Representing relations using digraphs. Definition: a directed graph or digraph consists of a set V of vertices or nodes together with a set E of ordered pairs of elements of V called edges or arcs. The vertex A is called the initial vertex of the edge A, B, and the vertex B is called the terminal vertex of this edge. An edge of the form A is called a loop. Example 7. A drawing of the directed graph with vertices A, B, C, and D, and edges A, B, D, B, D, C, A, C, B, and D. B is shown here. Examples of digraphs representing relations. Example 8. What are the ordered pairs in the relation represented by this directed graph? Solution: the ordered pairs in the relation are 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 3, 1, 3, 3, 4, 1, and 4, 3. Determining which properties a relation has from its digraph. Reflexivity: a loop must be present at all vertices in the graph. Symmetry: if x, y is an edge, then so is y, x. Antisymmetry: if x, y with x does not equal y as an edge, then y, x is not an edge. Transitivity: if x, y, and y, z are edges, then so is x, z. Reflexive: no, not every vertex has a loop. Symmetric: yes, trivially, there is no edge from one vertex to another. Antisymmetric: yes, trivially, there is no edge from one vertex to another. Transitive: yes, trivially, since there is no edge from one vertex to another. ADCB: determining which properties a relation has from its digraph. Example 1. Reflexive: no, there are no loops. Symmetric: no, there is an edge from it to B, but not from B to A. Antisymmetric: no, there is an edge from D to B and B to D. Transitive: no, there are edges from A to C and from C to B, but there is no edge from it to D. A, B, C, D. Determining which properties a relation has from its digraph. Example 2. Reflexive: no, there are no loops. Symmetric: no, for example, there is no edge from C to A. Antisymmetric: yes, whenever there is an edge from one vertex to another, there is not one going back. Transitive: no, there is no edge from A to B. ADCB: determining which properties a relation has from its digraph. Example 3. Reflexive? No, there are no loops. Symmetric? No. For example, there is no edge from D to anti-symmetric. Yes, whenever there is an edge from one vertex to another, there is not one going back. Transitive? Yes, trivially. There are no two edges where the first edge ends as the vertex where the second edge begins. ADCB determining which properties a relation has from its digraph. Example 4. Example of the powers of a relation: ABCDR, ABCDR2, ABCDR3, ABCDR4. The pair x, y is in Rn if there is a path of length n from x to y in R, following the direction of the arrows. Equivalence relations. Section 9.5. Section Summary. Equivalence relations. Equivalence classes and partitions. Equivalence relations. Definition 1. A relation on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. Definition 2. Two elements A and B that are related by an equivalence relation are called equivalent. The notation of B is often used to denote that A and B are equivalent elements with respect to a particular equivalence relation. Strings. Example: suppose that R is the relation on the set of strings of English letters such that R if and only if L A equals L B, where L x is the length of the string x. Is R an equivalence relation? Solution: show that all of the properties of an equivalence relation hold. Reflexivity: because L A equals L A, it follows that era for all strings A. Symmetry: suppose that arb, since L A equals L B equals L A, also holds in bra. Transitivity: suppose that arb and B are C, since L A equals L B and L B equals L C, L A equals L A also holds in arc. Congruence modulo M. Example: let M be an integer with M greater than 1. Show that the relation R equals AB mod M is an equivalence relation on the set of integers. Solution: recall that a B mod M if and only if M divides A minus B. Reflexivity: A mod M since A minus equals 0 is divisible by M since 0 equals 0 M. Symmetry: suppose that A B mod M, then A minus B is divisible by M, and so A minus B equals Km, where K is an integer. It follows that B minus A equals minus Km, so B A mod M. Transitivity: suppose that A B mod M and B C mod M. Then M divides both A minus B and B minus E. Hence, there are integers K and L with A minus B equals Km and B minus C equals Lm. We obtain by adding the equations. A minus C equals A minus B plus B minus C equals Km plus Lm equals K plus Lm. Therefore, a C mod M divides. Example: show that the divides relation on the set of positive integers is not an equivalence relation. Solution: the properties of reflexivity and transitivity do hold, but their relation is not transitive. Hence, divides is not an equivalence relation. Reflexivity: AA for all A. Not symmetric, for example, 2 4, but 4 2. Hence, the relation is not symmetric. Transitivity: suppose that A divides B and B divides C. Then there are positive integers K and L such that B equals AC and C equals BL. Hence, C equals at KL, so A divides C. Therefore, the relation is transitive. Equivalence classes. Definition 3. Let R be an equivalence relation on a set A. The set of all elements that are related to an element A of A is called the equivalence class of A. The equivalence class of A with respect to R is denoted by AR. When only one relation is under consideration, we can write A without the subscript R for this equivalence class. Note that AR equals SAS element of R. If B element of AR, then B is called a representative of this equivalence class. Any element of a class can be used as a representative of the class. The equivalence classes of the relation congruence modulo M are called the congruence classes modulo M. The congruence class of an integer A modulo M is denoted by AM. So AM equals A minus 2 meters, A minus M, A plus 2 meters, A plus 2 meters. For example, 0, 4 equals minus 8, minus 4, 0, 4, 8, 1, 4 equals minus 7, minus 3, 1, 5, 9, 2, 4 equals minus 6, minus 2, 2, 6, 10, 3, 4 equals minus 5, minus 1, 3, 7, 11. Equivalence classes and partitions. Theorem 1. Let R be an equivalence relation on a set A. These statements for elements A and B of A are equivalent. I arb E equals B E B equals proof. We show that I implies E. Assume that arb. Now suppose that C element of A, then arc. Because arb and R is symmetric bra. Because R is transitive and bra and arc, it follows that B are C. Hence, C element of B. Therefore, a B. A similar argument omitted here shows that B A. Since A B and B A, we have shown that A equals B. See text for proof that E implies E and E implies I. Partition of a set. Definition. A partition of a set S is a collection of disjoint non-empty subsets of S that have S as their union. In other words, the collection of subsets I, where I element of I, where I is an index set, forms a partition of S if and only if I does not equal for I element of I, Ij equals when I does not equal J, and a partition of a set. An equivalence relation partitions a set. Let R be an equivalent relation on a set A. The union of all the equivalence classes of R is all of A. Since an element of A is in its own equivalence class A, R. In other words, from Theorem 1, it follows that these equivalence classes are either equal or disjoint. So, A, R, B, R equals when A, R does not equal B, R. Therefore, the equivalence classes form a partition of A, because they split A into disjoint subsets. An equivalence relation partitions a set. Continued. Theorem 2. Let R be an equivalence relation on a set S, then the equivalence classes of R form a partition of S. Conversely, given a partition I element of I of the set S, there is an equivalence relation R that has the sets I element of I as its equivalence classes. Proof. We have already shown the first part of the theorem. For the second part, assume that I element of I is a partition of S. Let R be the relation on S consisting of the pairs X, Y, where X and Y belong to the same subset I in the partition. We must show that R satisfies the properties of an equivalence relation. Reflexivity. For every A element of S, A element of R, because A is in the same subset as itself. Symmetry. If A, B element of R, then B and R are in the same subset of the partition, so B, A element of R. Transitivity. If A, B element of R and B, C element of R, then A and B are in the same subset of the partition, as are B and C. Since the subsets are disjoint and B belongs to both, the two subsets of the partition must be identical. Therefore, A, C element of R, since A and C belong to the same subset of the partition,